Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab is a distinctive virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. Welcome to the world of light and its fascinating journey through different mediums. Today, we are going to understand how light bends, whether due to refraction or reflection, as it travels from one medium to another. Let's dive into this experiment to uncover the science behind these beautiful light effects. Let me open bending of light simulation for you. Each simulation begins with a game plan. This outlines the procedures, observations, and learning of the simulation. If you are a new user, kindly go through this section thoroughly to maximize your experience. Our main objective of this simulation is to demonstrate how light bends when it travels from one medium to another, and also to explore what happens when a light moves from the rarer to denser medium and vice versa. Let's begin by exploring how light behaves when it moves from one medium to another. Here we have a laser that you can position to send beam through various mediums such as air, which is single medium, and water, glass, and even boiling water, which are having different refractive index and n values. By clicking on this set laser position buttons, you can set the laser position to rarer medium or denser medium. In denser medium, you can pick up the options of vegetable oil, water, boiling water as a single medium, and in rarer medium you can select the medium as glass, water, boiling water, and single. By clicking on show labels, it will give you the name of the objects present over here: laser, glass, or water, whatever the medium present there, and the target material. Let's start with the glass, and I'm going to fix the laser medium as rarer medium. Now it's time to set the target position. By clicking on this center button, set target position, this will place a target where the laser will be aimed. Once the target is placed, you can drag this laser source by using your mouse cursor. By click, hold, and drag, you can position it so that the beam can hit the target through the medium. Here the medium is glass, and as soon as it is positioned, the simulation will calculate the incident angle, that is I, and the refractive angle, that is R, in real time based on the medium you have chosen. You can change the medium now also to water, boiling water, or single medium. Let me fix that glass for now. Now the I value, that is incident angle, 14, and R value is 9 degree. By clicking on the denser medium, you can also adjust the target and see the I and R values as well. But here is the exciting part of the simulation. You are not just going to watch the light, how light bends. You will measure the angles by yourself. For that, let us fix the medium and the position and the targets first. Now the medium is rarer medium, glass, and the target position, we have to drag the laser light to set the target. Now that the laser is ready, we are going to take some measurements. By clicking on this top right button, measure, it will take you through the experimental setup where you are going to measure the values. Now the laser is locked. It is asking us the question, what is the incident angle, refractor angle, emergence angle and rate of shift. First of all, the incident angle, this is the angle between the incoming laser beam and the normal, that is an imaginary line perpendicular to the surface, like this. And you can use the protractor to measure this angle. For using the protractor, you can use your mouse cursor by click, hold and drag. You can position the protractor in different angles. You can click on this arrow mark to rotate the protractor. Next, the refractor angle. Refractor angle is measured when once the laser enters the new medium, it bends. The angle between the refracted beam and the normal is called refracted angle. You can measure it using protractor as well. If you find it difficult to view this in this way, you can pinch your mouse or screen, or else you can scroll your mouse to zoom in and check the values of the protractor. Let me put 23 over here. Thirdly, emergence angle. If the laser passes through a transparent object like glass, it will exit on another side. The angle between the emergent beam and the normal is the emergence angle. This can be measured using the protractor as well. Let me put 5 degrees. And finally, it is asking us to measure the lateral shift. This is nothing but this is the horizontal distance between where the laser enters the new medium and where it exists. You can use the ruler by clicking on it to measure the lateral shift in centimeters. Let me put 0.5 centimeter. Once you have input the correct answers or out of the measured angles from this experiment, you can click on this check values button to view the answers. Now, as you can see, the red ones are the wrong answer and the green ones are almost right answers. And the correct answer for this experiment is provided over here from our Scholar Lab. That is 38 degrees 24 and came to 38, and the lateral shift is 1.3 centimeters. This can be varied depending on the laser position and the medium you have chosen. You can encourage your students to try it with different parameters by changing the medium and the position to get master of this experiment bending of light. By the end of this simulation, your students will have a thorough understanding of how light bends when it passes through the different materials and how to measure the angles and lateral shift and the science behind the refraction and total internal reflection. This medium behaves differently, and you have the tools to explore these behaviors hands on. So get ready to hit the target and measure like a true scientist. Let's bend some light and uncover the mysteries of refraction. Happy learning! Thanks for watching.